What's up, folks? This is Core Chapter 11, Probability. We're going to look at the first 6 sections in this video. It's nothing really too challenging, not super mathy. There's some new vocab. Otherwise, I don't think it should be too challenging. The rest of the chapter gets a little more exciting. Before we move on, though, I got to get this out. I think I'm pretty well known for trashing AP Calculus as being a pretty easy course compared to how much credit it's given. But the opposite's true for AP Stats. I love AP Stats. I think it's an amazing course, and perhaps you've already taken it. Perhaps you're taking it concurrently with this one. Perhaps you're going to take it next year. In any case, there's going to be a lot of overlap. So chapter 11, 12, and 13 from our core book, and then a few of the other chapters from the ANA-HL book. There's a lot that's covered in both this course and AP Stats, and of course, whichever one you see second is going to be a little bit easier because you've seen the material before. But what you'll find is that the two courses definitely emphasize different aspects of statistics and probability in different ways. So certain things are going to be really emphasized for IB and won't really be a main thing at all for AP, and also vice versa. So it's just something to keep in mind. Because I wouldn't want you to take one course lightly and not really give it your all because you feel like you've already seen the material, so it would be super easy. Because then that's how you could miss something and start digging yourself into a bit of a hole. In my videos on this topics, I'm going to include questions from AP as well as from IB because I want you to get a very well-rounded view of the topic. But I'll be sure to mention when something is coming from AP specifically so that you know. In general, the IB tends to be more of like an algebraic take on statistics and probability. There's a lot of formula use, a lot of calculator in both. But whereas AP Stats is really focused on what the statistics and probability means within the context of a real-world problem. Whereas the quote-unquote real-world problems that we end up seeing in AP and IB rather are they're pretty simple and seem very forced. Whereas AP, they seem much more like realistic. But I don't know, maybe that's just me, but I love AP Stats. It's one of my favorite courses I've ever taught, ever, and I definitely think that you should take it if you have the opportunity. Anyway, that said, we begin here with kind of a prologue to the chapter. So this is before section A even starts. Basic stuff for probability. If something is impossible, then it has a probability of exactly 0. If something is absolutely certain to happen, then it has a probability of 1 or 100%. And every other event out there has to have a probability somewhere in between 0 to 1. You cannot have a negative probability. You cannot have a probability that is greater than 1. That sounds obvious, I hope. But I mean, I've seen these answers given to me before, and I don't want it to ever happen again. So 0.5, that's equal chances of happening, it's not happening, and then we can have anything in between. Okay, when we determine probabilities in a situation, that could be based on one of two things. Either the results of an experiment, and I mean, we use this word experiment not like a scientist would, where we're setting up, things with we got like beakers and scales and all that. It's not like that. All that means is something is happening in the physical world and we are recording the results of it. That is an experiment. So if we do many experiments of the same kind, then we can generate a probability from that. That'll be called experimental probability. However, we can also base probability on just thinking about a situation, and we can come up with the theoretical probability for what could happen. And probability theory really does show up all over the place. So if there's a single mathematical skill that I think is important for all human beings to have, it would be being able to think about probability better, because our human brains were just not evolved for this stuff. And really, people are dumb when it comes to probability. So hopefully you will become a little more less dumb through this chapter. A little more less dumb and a little less ungood at grammar. Okay, section A. So, hey, look, vocab. All right, so we're doing an experiment. We're going to talk about the number of trials. That's how many times the experiment happens. The outcomes. Just what are the different possible results for each particular trial. Frequency. That's how many times a result happens. Relative frequency. That's making that frequency into a percentage out of the total. Okay, and so we have an example down below where we can see these words in use with this cone being tossed in the air. Great, so we define the experimental probability to be the relative frequency of an event happening. Wow, section A, that was so tough, all right? Section B, we got these things called two-way tables. Look, it's a table that has kind of like two categorical variables. So that's a big word, and we're not getting too into what those mean in this course. AP would spend a lot more time with that. In this case, the two variables are like what kind of person you are, and that variable could take on the value of either being a child or an adult. And then the second variable would be your feelings towards a ride at the theme park. And you can either like the ride or dislike the ride. So we have two variables, and each variable in this case could take on one of two values. And so look, you know how to read the table, right? There's 55 kids that like the ride, there's 28 adults that like the ride, etc. That's all obvious, right? And then we can use that to estimate some probabilities, because this is a sample. Yeah, this is just based on like a few people who were exiting the ride. They were asked how they felt about it, and we're going to use this sample to come up with a prediction about like what a random person at the park might feel about the ride. So anyway, okay, what's the probability that somebody liked the ride? Well, how many people liked it here? Well, it looks like 55 plus 28 out of the total, which is 130. And it's really helpful in these to come up with like to make a new row and a new column with just totals. We're just adding down the rows and across the columns, and then you can check to make sure that you get 130 both from these two and from these two. If you get a different number, then there's clearly an error somewhere in there. So anyway, that's how we could answer. The first problem, if we're talking about it being a child and disliking the ride, keyword there, and, then obviously we're just looking at those 17 people. So that's going to be 17 out of the 130. And then letter C, someone who is an adult or disliked the ride. So this is another keyword for us. We need to look at all the adults. But we also need to look at all the people who disliked the rides. And then notice that we double counted that 30. So we would not want to count it a second time. So it's just 28 and 30 and 17. So 75 out of 130. And we're on to section C. More vocab. So we've got the sample space U, and we've seen a capital U before. Back in chapter 2, we used the letter U to represent the universal set, which was a set of all elements that were under consideration in a given problem. And so you can see there's a connection now between probability and sets and Venn diagrams. Here, U is going to represent the set of all possible outcomes of an experiment. And we're going to define an event to be, okay, a set of outcomes that have a particular property. Really, I mean, that could be just a single outcome, or it could be a group of outcomes. That's kind of vague. So let's just say we were rolling a normal dice with 6 sides, yeah? So we could call an event might be rolling a 5. So that's a single outcome making up the event, or the event could be rolling an even number. So there would be 3 outcomes making up that event. Down below, we have complementary events. Now, their probabilities must add up to 1. So, for example, outside the realm of quantum mechanics, a person must be either dead or alive. So the probability of a person being dead plus the probability of a person being alive must be equal to 1. So we're back here again with the normal 6-sided dice. We're going to roll it, and we're going to have our event that we're interested in is that we're rolling a prime number. So of course we need to know what the prime numbers are on that dice, and they will be 2, 3, and 5. So we're going to use set notation here. What is the sample space U? Well, obviously, I mean, that's just going to be all 6 of the numbers on the dice, so that's pretty obvious. What are the events in our what are the outcomes in our event A? Well, I've already listed them. They're 2, 3, and 5. And then, of course, the outcomes in event not A must be 1, 4, and 6. And here is a Venn diagram, which is a very boring Venn diagram indeed. So there's a couple other ways that we can organize our thoughts. One is a 2-dimensional grid, seen at left, and there's a tree diagram. Tree diagrams in particular are going to be very, very useful for us throughout this course, so I really like to employ them whenever I can, but I don't know, some people like grids, I guess. Here you'll see that we're representing the same situation twice, so we're just flipping 2 coins, and we know that we could get, if we flip 2 coins, these are the only 4 outcomes that could occur, right? Heads, 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 tails, tails, heads, or tails, tails. And we see that here in the grid, it's like coordinates. So this is getting tails on the first toss and heads on the second toss. And that would be like this outcome right here, where we get tails on the first and then heads on the second. And then we write that out over here as tails, heads. And the reason, of course, that a tree diagram is way more useful than a 2-dimensional grid, I mean, hey, it's in the name. A 2-dimensional grid is only 2-dimensional. So if we wanted to flip the coin a 3rd time, the grid would need to like pop out of the board into 3D space, whereas our tree diagram could just create more branches. Okay, so here we have a tree diagram showing when we have 3 events, one after the other. So we're spinning the spinner 3 times, and we're recording whether it's blue or white. Wow, this some advanced stuff here. I promise it gets more exciting. We're just taking some baby steps because we can't just jump into hard problems right away with tree diagrams later on. So yeah, just bear with me, all right? Anyway, we're on to section D now, which is theoretical probability. So I said before, that's when we just kind of like think about the problem and know what the probability should be. But this requires that each of the outcomes are equally likely. And then all it is we take the number of outcomes in our event divided by the number of outcomes in the sample space, and that gets us the theoretical probability, which we write as P of A. So, okay, classic probability question. We've got a basket or a bag or a bowl or an urn, and it's got a bunch of things of different colors. Classic. Okay, what's the probability of getting a green ticket? How many tickets are there in total? Looks like there's going to be 12 in total. How many are green? 3, so letter A should be 3 out of 12. And then letter B, green or yellow. Or means we're going to add things up. So there's 3 greens and there's 4 yellows. So there we go. Orange. Wait, there were no orange tickets. Okay, probability of 0. And then green, yellow, or blue. Again, we add up the greens, the yellows, and the blues together. And we get 12 out of 12. So we got to get one of them when we choose the ticket. Here's back to our 6-sided dice. What's the probability of getting a 6? Well, there's only one 6 on the dice, and there's 6 options, so that seems like it should be 1 out of 6. Not getting a 6 is therefore 5 out of 6. Now, you could think about that as listing them out. There's 5 outcomes within that event, so therefore it's 5 out of 6. Or you could say, hey, 6, not 6, those are complementary. This probability is 1/6, therefore this probability has to be 1 minus 1/6, which is 5/6. And then we can do that again with these other 2. Getting a 1 or a 2, so we add up. There's one outcome of a 1, there's one outcome of a 2, so that's 2 out of 6. Therefore, not getting a 1 or a 2 has to be 4 out of 6. Okay, this one's a little bit more exciting. So we've got a class. It's back to Venn diagrams from before, right? This is much more thrilling Venn diagram than the earlier one was. So we'd have to make our Venn diagram. Again, we start in the inside, so we know 15 study both. So that's how we get that there. We're told that 17 study chemistry in total, so that's going to be 15 plus 2. And likewise for physics, that'll be 15 plus 4 to get 19. There's 30 in total, so we add up those 3 numbers that are just underlined, and we realize that there's 9 left over who don't study any of those things. And once we have them listed out, then we can calculate the probabilities pretty quickly. How many study both subjects? Well, it's got to be 15 out of 30. How many study at least one? So that's going to be all 3 of these added together. How many study physics but not chemistry? So that's just going to be the 4 who are in the physics circle but not in the center, and so on. I think we see where this is going, yeah? Okay, section E. Now we're talking about using probabilities to make predictions. And you can read this thing here about the algebraic explanation for it, but you know this already, right? So back to the dice. Probability of rolling 5 is 1 out of 6. So if I roll the dice 60 times, how many 5s should I roll? Well, it's going to be 10, right? Because it's 1/6 multiplied by 60. You knew that, right? So the formula that we're using is we multiply n, which is the number of trials, multiplied by p, which is the probability of our whatever event we are interested in, and that will give us how many times we expect the event to occur. Please note that this is not guaranteed to be an integer, even if the data are all integers. If I'm only rolling the dice one time, then the probability of, or excuse me, the expected number of fives is going to be 1 out of 6 fives. Like 1/6 of a 5 is the amount of times I expect a 5 to show up on that one roll, which it sounds weird, but that is mathematically correct. And I would advise you to give answers to this type of question as rational numbers unless a problem specifically says to round to the nearest integer or something like that. Sometimes the way a question is phrased, there'll be like an inequality implied, and so there you could like round it up to or down appropriately to an integer. But if we're just being asked, hey, what's the expected number, then just give it as a decimal. Now that being said, here in this next example, the book disagrees with me. So we've got Michael Jordan, we've got his career percentage from the free throw line. How many shots would we expect him to make if he took 18 more? Well, it's going to be 18 multiplied by that probability, change from a percentage, of course, to a decimal. And so I would give, well, 15.0 rounded to 3 significant figures, right? The book just said 15. There's nothing in this question that says that it should be an integer, so I think the book's answer is wrong. These publishers have made many glaring errors in the past. I am expecting this problem to show up in their published errata whenever they come up with it, but it's not out as of me shooting this video, so I have nothing else to say about it. All right, moving on. Oh my gosh, we're in the last section. This is so exciting. So compound events. This one, there's going to be more than one event happening, yeah? And we've actually already seen some examples of that in this video. Compound events are going to have the words and or the words or in it. So if we're interested in an event of both A and B occurring, the notation is like that. So that symbol is, we can read that as A and B, or we can say A intersection B. And the probability for A or B, which this is really important in mathematics, when we use the word or, we mean or both of them. That's written using this symbol here, and we read that as A or B, or just A union B. So I think the way to remember this is union the symbol clearly looks like a U. Intersection, the symbol kind of looks like an N maybe, which is like in the word intersect. It's in the word union too. I don't know. Just remember what the symbols mean. And we have formulas here. The probability of A or B is equal to the probability of A plus the probability of B minus their intersection. So remember this problem here when we had an adult or disliking the ride. I looked at the adults, I looked at disliking the ride, but then I had to subtract away the intersection because it was going to be double counted. So that's exactly what's happening here. And last vocab on this page, two events are considered to be either disjoint, or we say mutually exclusive events if they cannot both occur. So the probability of A and B is exactly 0. And so we can leave out that last bit about the intersection. All right, the IB loves problems like this. This is all just about formula manipulations. I'd practice a lot of these if I were you. So as soon as I see something like this where they're giving me values for probability of A or B and probability of A and B, I'm immediately going to write down the formula we just had on the previous page. I'm just going to fill in things wherever I can. So there it is. And by the way, I should point this out. Oftentimes you'll see it with those two just interchanged. Of course, that makes no difference. But anyway, now we can fill in, we know the probability of A, we know the probability of A and B, and the probability of A or B, so that makes this one really simple. We just solve for probability of B. There are certainly some more challenging ones out there, but I'll save those for class. And final example for this video, What do we do with something like this? Well, first of all, part A, are A and B mutually exclusive events? Well, yeah, you can't score both an A and a B on the test. There will be students who score A and other students who score B, but a particular student cannot score both an A and a B. So those are definitely going to be mutually exclusive events. Now, given that, we can start to fork out some of these other things. So probability of A, well, there's 7 getting an A out of 30 students, so that's 7 out of 30, and likewise B is going to be 11 out of 30. The probability of A and B is 0 because we said before they were mutually exclusive, and then we can use our formula to work out what the probability of A or B is. So that's it for these sections as far as like the core content. Like I said, there's definitely harder problems, especially with the formulas that we'll practice. But for the rest of the stuff, it doesn't really get that much harder until we start seeing more content, but that comes later in the chapter. So this is a good foundation for probability for right now.
So it might have bugged some of you earlier in this video that I was referring to this singular object as a dice, and I'm sorry, but I'm going to continue doing that. And here's why. In fact, it's today's quotation, which is attributed to one of my favorite YouTube mathematicians. His name's Matt Parker. He's super smart and hilarious, and I've met him in person. It was one of the best nights of my life. But anyway, in one of his videos, which I couldn't figure out which one it was, I actually wanted to show him saying the quote, but he has so many videos and I'm not sure which one it is. But anyway, in one of them, he was continually referring to this as a singular dice. And he said it's because Matt Parker, and I will now take this on for myself, it is a singular dice because Mr. Ropke never says die.